really surprise you
at your
that he
audition.
forgot.
We hope it's going great.
We know it's going great.
We know it's
You all are so supportive of each other. I like it. Okay.
We like it.
Today we're going to talk about both area and arc length.
We're talking about
Hey. So, for a moment, you're just going to sit back and relax.
that's what I'm talking about.
Okay?
Yep.
And just kind of go through with me why polar area is the formula that it is. There must have been some update, and some of my, any symbol that I had is now a box, and so just
Oh wow.
bear with me.
Oh
Okay.
wow.
All right.
The theta's there.
So, well, down here. Okay. The length of an arc in a circle. So if we have a circle and we talk about the arc length, right? Okay. The arc length is given by r times theta. Okay. That is something you learned in Algebra 2 and in pre-calc. Okay. It's okay if you don't remember. Okay. When theta is given in radians. Okay. So arc length is r times theta. So let's just imagine we have a very, very small theta. And so it is so small that it basically looks like a triangle. Right? If I cut a small enough sliver of a circle, it's pretty much a triangle. Right? Because there's not as much curve if it's small enough.
Yeah.
Okay. So if we're talking about a triangle, we're talking about 1/2 base times height. Well, if this arc length is r times theta, but we're so small, we're talking about d theta instead of theta, okay, then that means our area is 1/2 base times height. So we're talking about 1/2 r squared d theta. And we're talking about differentials because we're talking about such a small change in what's happening. Process it. Are we okay? All right. Well, what are we going to have to do? If I'm talking about the area of a polar curve, I'm talking about lots of slices of triangles that we're going to have to add together. So what do we do? A summation, which means we're going to need an integral. This is how we find the area. This is what you can write down now. The area of a polar curve is the integral from alpha to beta of 1/2 r squared d theta. Bless you.
Thank you.
Because we are basically summing up all of our itty bitty triangles of 1/2 base times height that we're then adding together.
That makes sense.
The biggest thing is remembering that darn 1/2. Okay? Also, so this in itself really isn't that bad. What we're going to have to be careful with are our limits of integration. Where do we start? Where do we stop? The good news is a lot of our curves are symmetric. And we can use symmetry to help us have a shorter range and help us with some of our evaluating. All right? So let's just get right into it. I want the area enclosed by this cardioid.
That's like a tomato.
Yeah.
That's better.
Don't you know all hearts look like tomatoes?
Yeah, why is it not? Why is the 2 not distributed? It's not just form.
You can write it distributed if you would like.
Oh.
Okay? In the book, you might encounter problems like this, which is why it's written up there like that. Just go ahead and distribute it out so then it's easier to work with. Okay? All right, well, let's talk about this. We know that a cardioid is drawn from 0 to 2 pi, and it is fine for you to make your integral set up from 0 to 2 pi. hand sanitizer?
Yeah,
I did.
Oh, is that one?
Oh, man. Okay,
Yeah.
my nose was burning.
You sure?
No, you definitely smell like pine stuff.
Okay.
Okay, this would represent our area. What else would represent our area?
We shaded in the graph.
True.
Half of it.
Okay,
Times two.
we could take the integral. We could take the integral from 0 to pi and multiply it times 2.
So it just be 1.
But isn't it 0 because the top's the same as the bottom? Wouldn't it be negative on the bottom?
So we're talking about the area in between the curve and the x-axis, and so it's going to be positive area all the time.
Isn't it below the x-axis?
Absolute value there.
But it's area between curves, so we're talking about positive area.
Okay.
Because we're basically, what's happening is we're adding up all of these itty bitty triangles from the pole. Like
Oh.
this.
That's negative distance away from the okay. That makes sense.
So we're taking all of these triangles
That looks really cool.
and adding them together.
Yeah.
It's a seashell.
It's like a
It's
shell.
seashell.
Be
Or a lily pad.
No,
Well,
it's
what
a
if
seashell.
one area is doing negative all?
No.
Okay.
More of it.
Would that be negative?
Okay, so this is what I'm going to do. What's 2 squared?
4.
4.
I got that one.
Yeah.
I'm going to take this 2 squared and take it out.
Get out of there.
So this becomes 2 integral 0 to 2 pi, because 4 times 1/2 is 2.
what?
Wait, how are you able to take the 2 squared
Okay,
out?
you know what? I'm not going to do that.
Yes, you are. No,
Yeah.
yes, you are.
Yeah.
It's fine.
Yeah.
Okay, I understand.
You just take it 2 out.
Factor of 2 squared, 4 times 1/2 is 2.
Okay.
Keep up, Caleb. Let's see how-
So now I have 1 plus cosine the quantity squared. So we have 1 plus 2 cosine theta plus cosine squared theta. And here's where all of your work with trig integrals is going to come into play. Why did we have to do all of that? Well, so you can do polar here. All right?
You know what?
We
That actually
can-
makes sense.
We cannot take the antiderivative of cosine squared. Instead, this came up in one of our problems on the final. We have to change it to 1/2 plus 1/2 cosine
This
2
is the one
theta.
I wrote.
Yeah, power.
So now we can take the antiderivative. Bear with me here. 1 plus 1/2 is 3/2. Do you agree? So antiderivative 3/2 theta.
Wait, what's it?
Yeah, say it again.
1
Yeah.
plus 1/2 is 3/2.
Yeah.
Its antiderivative would be 3/2 times theta.
Okay.
2 cosine theta. Antiderivative is
2 sine
2
theta.
sine theta. Okay. Okay. And then 1/2 cosine of 2 theta would have an antiderivative of
1/4 sine 2 theta.
from 0 to 2 pi.
How did you? Can we go back real quick?
Uh-huh.
How did you get from 2 plus 2 cosine theta squared to the 1 plus 2 cosine theta plus cosine squared?
So if we think about the 2 factored out,
I see how the full, like how you. put the
okay,
2
so
out.
then I have 1 plus cosine theta. If we FOIL it, because it's squared,
Oh, okay.
1 plus cosine theta, the quantity squared, is this trinomial. Okay. Awesome. Then we get to plug in our limits of integration. So we have 2 times we're going to plug in 2 pi minus, we're going to plug in 0. So our area is 6 pi. Right.
Extremely loud and critical.
Have you read that, Miss Owen?
It's sad.
It is very
It's
sad.
very sad.
I don't know if I can read another.
There's literally.
So I read a book
It's a
this summer
reverse
called
romance.
Torn about,
Is that the one about mental
no,
health?
it's about the tornado that comes and like wipes out her entire town,
Oh,
and then she gets like,
I get it, because tornado, torn.
yeah.
I get it.
And then I read,
It's okay, we're here for you.
it's a book, and I can't remember the name of it, but it's about a girl who goes to Omaha Central,
Oh, that's
and
weird.
it's like a back and forth book where it's written in the perspective of the boy and the girl and the boy. Anyway, it doesn't matter. We gotta get to this. Okay, question. And then I read the book where the crawdad scene about a girl who basically gets abandoned in the marsh and
Crawdad scene?
sing. Like,
Oh, where the crawdads sing.
yeah, like her family abandons her in this shack in the marsh, and she grows up taking care of herself.
Crawdad boils are pretty good.
All right,
Should know a lot of that.
let's talk about this one. Go ahead and write it down. The area of one petal.
Just one?
PETAL. R equals 3 cosine of 3 theta. And this is where our knowledge of the graphs are going to help save us time. Okay, that's why we worked on them for so long.
Rose curve with 3 petals.
3. Okay, now if I want the area of one petal, what we need to know is where a petal starts and stops.
Where does it start?
Okay, so what would be important to know about this rose curve?
Zeros.
The zeros, how many of them are there?
3.
There are 3. So if we find the zeros, we really want to know where is the cosine equal to 0. The cosine is equal to 0 at pi over 2, 3 pi over 2, and 5 pi over 2.
So let's do pi over 6 and pi over 2.
Now, we can think about this also. We know that if, and you can start at pi over 6 and go to pi over 2.
You can start at 0.
You can start at 0 and find the area from 0 to pi over 6 and multiply it by
2.
2 because it's half of a petal. So we can take the area from 0 to pi over 6 of 3 cosine 3 theta squared and multiply it. By 2.
Miss Coleman?
Yeah.
Could you in general just divide 2 pi by the number of petals and get like the rate?
No.
No? It's sad. I was hoping so upset at some point.
That's not cheating.
It wouldn't be cheating, it'd be cool.
Okay, so what's 3 squared?
That's 9. Wait,
And
two
you just-
times 2 times.
You
Oh,
just
that's
do it up.
1.
2 times 1/2 is 1.
It is.
Gone. 3 squared is 9. So I just like my constants out front, so I don't have to worry about them
That's smart.
until the end. Okay, and then we have cosine squared of 3 theta. Once again, we're at a cosine squared. We can't take the antiderivative of that. So we would have to change it to 1/2 plus 1/2 cosine of 6 theta. We double the angle.
How?
Was that a how or just a noise?
No, that's a how.
How?
Is that the rule?
Yeah, so cosine squared x is 1/2 plus 1/2 cosine 2x. So whatever that angle is
Doubles.
gets doubled. So what we have is 9 times 1/2 theta plus 1/12 sine of 6 theta evaluated from 0 to pi over 6.
That's what I got.
And we are all very capable of plugging in values. No. You don't want me to stick to the answer?
Oh, yeah.
I'm just trying to save some time. 3 pi over 4.
That's the area right there. One pedal. Very cool.
Okay. So don't write this down quite yet. But remember when we talked about arc length? Okay. We started with this, where just like a little bitty piece of the arc length was Pythagorean theorem, square root of dx squared plus dy squared, changing x, changing y. Okay. Well, if we go to polar form where x equals r cosine theta and y equals r sine theta, I'm not going to bore you with the details, but eventually we would get to this right here. So in the red box is what you need to write down. Our arc length in polar form would be the integral from alpha to beta of the square root of r squared plus dr d theta squared.
That's
So,
what-
if you do some finagling with your algebra with that dx squared plus dy squared, it would eventually come out to this. Is it okay that I don't go through that today?
Probably not.
It's fine.
I feel like if we have time, we will.
Yeah, we'll go. When do we get out? 45?
Yeah.
Yeah,
We can stay after into lunch.
Yeah, let's do that.
Yeah, I'm.
Because we don't want to
even go
eat
to lunch, so.
for our diets.
If I really thought you were interested, Richard,
I would totally do that.
I have to eat my lunch.
See, she's
Well,
not
I
a
don't even
dedicated
go to
teacher.
lunch, so we can all wait.
Your
Math
time, I'm
first,
sure, would love
food
to
second.
Someone is
I have first lunch and second time, and Miss Hahn's time is in here while I'm eating lunch, so I'm not even in my
Well, then have Miss Han teach you.
Who's Miss Hahn? Who is that?
She teaches geometry.
She
She has really short hair.
She knew.
Nope, she's been here since the building opened.
I don't know
Oh.
who that is.
Ouch.
Yeah, I
I
think
can
from my
see her
advisement.
what she is.
Her and Miss Jacek were the ones that
Who is
were.
Miss Jatsick?
Never mind.
She's
Miss
a jerk.
Jackson has a lot of tech problems.
They were the ones that were organizing the tech room.
Huh?
Just never mind. Okay. Here I have another cardioid, and I want to know the arc length above the x-axis. Okay, so what are we talking about? We're talking about our integral going from where to where? Okay, angles maybe?
From 1 to -1.
Angles? We're in polar.
We're gonna have to do some math.
0 to
Zero
pi.
to
Okay, now because I know how this is going to go, I'm going to go ahead and set this up from 0 to pi over 2 and double it.
Why is it 0 to pi?
Because this is the angle of 0 and this is the angle of pi.
But how can r be -1?
What?
Because at, what do you say, pi, is the
Mhm.
sine of pi 0.
0.
So what r would be 1.
So
that's
at
negative
pi,
12.
well, okay, so this is Cartesian numbers. At pi, we
Oh,
move
okay.
forward 1. Does that make sense?
Yes.
All right,
Just
so
what you should-
in our integral, we have the square root of r squared plus dr d theta squared. Well, what is the derivative of r with respect to theta? Sorry, I thought that was a simple one.
I mean, it was.
That was past my
yeah, she was kind
Oh, I
following the lead of my students.
When have I ever been passive aggressive?
Never. When is that what teachers are supposed to do?
No,
Are we doing what students are supposed to do?
special case today.
That's what students are expected to do, though.
Okay, so what do we have? We have 1 plus 2 sine theta plus sine squared theta plus cosine squared theta.
And we
Wait a
just
second.
substitute. We just substitute, right?
Wait, I gotta say, you can take that sine
Just
squared and
let
that one
people write it down and catch up.
cosine.
Can we also then pull out the radical two?
Uh-huh.
And it's squared.
What?
So sine squared plus cosine squared is 1,
Sure
which
is.
means we have 1 plus 1, which is 2. Sounds so simple, right?
Yes.
Okay.
Yes, it actually is.
Yes, we have a 2 underneath that we can factor out, but the 2 has to stay under the radical.
Yep.
So yes, we can come over here and take out a radical 2 so that we are left with radical 1 plus sine theta. And unfortunately, ladies and gentlemen, we are stuck at the moment.
All right.
Give up.
We are not going to give up. But
We tried, yeah.
so we can't use U substitution because we have a composition but nothing multiplied to it in order to be able to help us with our du. So instead we're going to have to use a strategy in 3.5 minutes. And what we're going to multiply by is 1 minus sine theta under a radical. Why would that be helpful?
Cosine.
Because 1 minus sine times 1 plus sine is going to give us the difference of squares 1 minus sine squared. Write it down.
I wrote it down.
I did too.
It's gonna get mushy.
It's I didn't like it. A little mushy.
That was great though, wasn't it?
I love Daniel.
I don't think he's in our time anymore.
He's not.
Is it?
I don't know.
So what happens is we have the square root of 1 minus sine squared up top and the square root of 1 minus sine in the denominator. Okay.
I really don't like that.
Well, eventually there's not going to be. 1 minus sine squared is cosine squared. And the square root of cosine squared
Holy cow.
does in fact equal cosine since we're between 0 and pi over 2.
You're telling me there's an instance when it doesn't equal cosine?
It would equal negative cosine if we were in the second quadrant, which is why I stayed to 0 to pi over 2.
Oh.
Okay. Wow, this is going really fast.
Keep zooming. We got like 1 minute.
Okay? We're not going to be able to finish this problem, but we now can using U substitution. U equals 1 minus sine theta. Du equals negative cosine theta d theta, which, boom, there's cosine theta right there.
Oh my god.
I gotta say, guys,
Okay? Now,
good job, everyone.
I would love to finish out this problem, but unfortunately the pep rally took like 10 extra minutes. So,
Post a video
Yeah.
for us.
Yeah.
But it's okay. That's cool. That's what.
okay? Enjoy your weekend.
We're sorry that we didn't finish it, Marina.
Why would you do?
I'm sorry, Marina.
Just go pure.
Well, we also wait